Hi everyone. In this video we're going to talk about the other data types, or what at least I call the other data types. We've talked about our major types of data that we're going to look at in this class, which are the usual sort of things that you see. So numbers, of course, and then you also learned about, I guess, numbers with decimals and numbers without decimals. You have your basic structures in R, so the numeric, integer, logical, string. And so we spend a lot of time on those, although you don't really need to spend time on regular numbers, but we spend a lot of time on strings. And now we're going to go to the other sort of non-standard data types that you'll see in data science, in R, in Python, wherever. And so we should talk about them. So strings. So we'll start with factors, then we'll go to dates, and then we'll go to spatial data. So that's what we'll talk about. Factors, and the package that works with factors is called ForCats. And so you saw on the first page here, ForCats is the left one. It's the best hex sticker, maybe in my opinion, because there aren't any dogs, but there are cats. I like dogs more than cats, but there aren't any dog ones that I know of yet, so cats are the second best. So ForCats, which is a box full of cats, is on the left. And then time, dates and times with the Lubra date, and then spatial data with this package called SF. Okay, so we're going to talk about factors with ForCats, dates and times with Lubra date, and spatial data with SF. Okay, and then we'll talk a little bit about maps with a package called ggmap, but you can do also maps with SF. So we'll see what that is in just a second. But we'll start with factors. Now, strings, I started before I got off on a tangent. I started talking about strings. Strings are, if we use statistical language, strings are categorical data. So we have like categorical and quantitative data. It is not quantitative, it is categorical, and we would call that also nominal. So strings in general are categorical, and I would call them nominal because they don't have an order. So eye color is categorical and nominal because you could have blue eyes or green eyes or brown eyes, so on and so forth. And there's no order associated. So they clearly aren't numbers. They don't have units associated with them. And there's no order inherent to eye color. So like blue is not better than brown, which is not better than green. They just are there. So that's nominal. But what if we have data that is categorical and ordinal? When we have categorical ordinal data, and we do have categories, so again, it doesn't have units associated with it, but there is an order. You could think of military ranks as categorical ordinal traditionally. Grades, not in number form, but in letter form, A, B, C, and D. Although you may argue that there are units associated with those. What year you are in college, first year, sophomore, junior, senior, super senior, so on and so forth. So any of those that have order associated with them, we have to treat them a little bit differently. In R, they call them factors. You may have come across factors when you're trying to make a plot in the Data Science 3 homework or something like that. I've seen a couple of you use it there, or you may have just seen it elsewhere in your searches. And so a factor is like I say, semi-basic here. It's not really one of the basic ones, but it does exist in base R. We're not coming up with something new here that didn't exist in the sort of base distribution of R. And they're used to represent categorical variables. At a basic level, a factor is a vector of integers with associated levels, which are characters. So when you actually look at a factor, it's going to be a bunch of integers. And so if we looked at college years in, well, not years in college, but what your classification is: first year, sophomore, junior, senior. The actual structure underneath would be a vector. And if you were a first year, you would be a 1, a sophomore would be a 2, junior 3, senior 4. So you'd see like 1, 2, 3, 4, or any sort of 1, 1, 2, 1. As you go on, however many people you have in the data set, each one is going to be associated with 1, 2, 3, or 4, which is first year, sophomore, junior, senior. And then they have levels, which are characters. So levels are the first year, the actual string that would say first year, sophomore, junior, and senior. So, for instance, here I have eye colors, and I make it a factor, and you can do so with the factor function. Although we aren't going to do that, we're going to use stuff from ForCats, which is a little fancier. But this is just a basic thing. I'm making a simple factor, which is called eye color, and it has blue, green, brown, blue, brown. Okay, and so when I look at the structure of eye color, you see that it has a factor. So it says it's a factor with 3 levels. So it identified 3 levels: blue, green, and brown, just from what I wrote. And it shows that blue. So it shows you blue and brown, but there's one more comma and some ellipsis after that. And so you can imagine that green is going to be the third one. It looks like it did it by, it sort of grouped them by alphabetical order. So it went blue, brown, green. Okay? So it didn't do it by what it saw. If it ordered them by what it saw first, it would be blue, green, brown. But it did alphabetical order, so blue, brown, green. And it shows those 3, 2 and ellipsis. And then it shows you what the actual vector was underneath, which are those integers: 1, 3, 2, 1, 2. So 1 goes to blue, 3 goes to green, 2 goes to brown. Okay, and so anyway, that's the structure of a factor. Factors are useful in a couple of different areas. One is when you want to use categorical variables in a modeling setting. Now, we don't really have a good idea about what that is, at least in terms of knowledge that you've learned, particularly from this class. You may have modeled before. Or you certainly have in other classes, although you may have not called it modeling. But anyway, in terms of this class, we haven't learned enough yet to get there to understand why they're useful there. But what we do understand, or what we can use factors for, are when you want to display character vectors in non-alphabetical order in a plot. Okay, and so this is, I guess, a wink, wink, nudge, nudge. You'll need to use factors in part 4 of our homework 4 if you haven't got there already. So, ForCats is the Tidyverse package for working with factors. Like all of the other packages, the function names start with a certain 3 or 2 letter specification. And they all share the same sort of format, and you do 4 things with ForCats. If you have to put them in sort of bins, there are 4 bins that ForCats does stuff with, and that's creating, inspecting, or combining factors, changing level orders, changing level values, and adding or dropping levels. So all of these things you may want to do with your factors. Okay, so here are the functions which go with each of them, and so you see all of the functions start with FCT, or factor, and then the verb of what you're actually doing to the factor is second, and so that's the sort of tidyverse-ness of those function names. Okay. And so creating, inspecting, combining factors: FCT count, FCT unique, FCTC, and FCT unify, and then you go on, so on and so forth. Okay, and so I'm not going to go through them all. That would take forever, but I do want to go through a couple of them where you might see a couple of plots and how I can use factors to change those plots. Okay, here's a cheat sheet. As always, they might be helpful. They're pretty helpful for factors to see what's going on and see what each of those functions do. Okay, and so here are the use cases. So, for instance, I have some data from the General Social Survey. So the GSS CAT data. You can see that I'm working with, and I'm doing something with religious summaries there. But the GSS CAT data set comes from the 4CATS package, so it's the data that they use to do examples from, and so I'm grouping by religion and summarizing age, TV hours, and the number of people who said that they were that religion for each of them, and I get this plot. And so for each religion, here I'm just plotting TV hours versus religion. So TV hours on the x-axis, religion is on the y-axis, and there are a lot of religions, and it looks like if you don't know, there's a lot of people, well, there's some people who say you don't know, and they seem to watch TV a lot. And then the rest of it's kind of hard to see because there are a lot of religions, and a lot of them are kind of close to each other. And so it could get lost in sort of following the line over to see what religion it is. You can get lost. So it might be a good idea here. What if I want to change religion? So I want to change that religion, the y-axis, maybe from highest to lowest TV hours, so that I can compare easily without having to sort of match X and Y position. I know if you're below, if I change it so that the highest average number of hours are at the top, if I go like highest to lowest, then I don't have to sort of do some eye straining to see what I want to see. So let's try to do that. Okay, and so here's the plot that I'm looking for. How did I get there? So I use the same aesthetics, but if you look in the Y aesthetic, instead of just saying religion or RELIG, I use this function called FCT_reorder. And so it says I want to reorder religion, right, which by default, if we look before here, we sort of, there doesn't seem to be any rhyme or reason. It doesn't go in alphabetical order. It doesn't really go in any order, so maybe it's what it saw first in the data set. For some reason, this is how it showed up on the y-axis. Okay. And that wasn't really helpful. And so if I want to reorder those based on another variable, a quantitative variable, so I want to reorder a qualitative or a categorical variable based on the quantitative variable, I can use this FCT_reorder to reorder religion by TV hours, and it gets us what we want. Another example is this. So here I have a bar chart of how many people said their marital status. And so again, it might be helpful to go from highest to lowest. This is a little bit easier to read probably than that last graph. There are only 6 different categories, and they are fairly different. But if I wanted to go lowest to highest, highest to lowest, I can use here FCT_infreq, so about frequencies, to reorder from highest to lowest. Now that wouldn't have worked in the last case, because here I'm just plotting counts of marital statuses. Before I had 2 variables, and I wanted to reorder one based on another. Yeah? Okay. So there are 2 different cases in which I find factors helpful. You may find others along the way, but I at least know one of them, either this or either the reordering or the infrequency is going to help you on one of your homeworks. So you want to pay attention to that. So now we go to dates and times. So dates and times are very simple, or they seem simple at first, but they can get quite confusing and hard to work with. Okay, so you can have date and time objects in R. Again, they're sort of semi-basic. They're not the basic double, integer, logical, character. They're not those four basic ones, so they have a little bit of extra stuff going on with them. These dates and times can become challenging because you have to really reconcile physical phenomena like the rotation of the Earth and the orbit around the Sun, and you also have to consider other geopolitical issues like months, time zones, daylight savings time, etc. So when you think about dates and times and you're working with dates that go back 50, 60, 70, however many years, 2,500 years, or whatever you have, times, you have to worry about leap years, and you have to worry about all of this kind of stuff. Another thing you have to worry about, that we'll get to, is that people write dates and they write times differently, and you have to reconcile that as well. And so R has pretty good basic support for dealing with dates and times, but like other things in R, they're not so I want to say equal. They don't follow a general pattern in what the name of the function is, sort of how they work, and they can be a bit odd, as I say here. Lubridate offers a unifying structure. Again, that's what every sort of tidyverse package is doing. The stuff exists in base R, but it may be a little bit odd to work with, and so they're trying to give you helper functions that have a structure that's easy to understand. So what do dates and times in base R look like? So here is a date, June 3rd, 1993. This is my birthday, and so I want to make that a date. So I give it as a character, just a character. It doesn't know any better than it was a character of 1993-6-3. Okay, but if I use this as.date, this conversion function, it gives it to me in this, which is slightly different, but you see it adds 0 and it adds a 3 there, and so it's done something. It's done something. So what if I try this? So as date wasn't that exciting. It gave me something slightly different than what I put in. But what if I try to subtract dates? So there's my birthday on the left and my wife's birthday on the right. So what's the difference between our birthdays? Does this work? And it turns out it does work, and it even has a fancy printing method that it tells you the time difference is 81 days. So we were born 81 days apart. Okay. And then I have something a little bit different. So that's date. And then we have this POSIX, or I'll call POSIX LT. So we have this POSIX LT thing. And when I ran this function, it was March the 10th, 2020 at 12:30 p.m. Okay. And so to show you that. Now here's the cheat sheet for dates and times with Lubridate. Lubridate has a lot of functions. Most of them deal with parsing dates and extracting important information like the duration between two date or time objects, etc. Okay, so for instance, we have this. So there's a now function. Again, I ran that at 1:38 on March the 10th, 2020. Okay, then you have a bunch of different parsing functions. So month, day, year, so MDY, but I could have day, month, year, month, date. All of those are separate functions in here. And then you get even crazier. You have month, day, year, hour, minute, second. So if you have a date and time. Okay, so we aren't going to do a lot with dates and times, but they are there, and you may want to use them for your final project. So at least I give you a little bit of an introduction to those. Now, I do want to talk a little bit more at length about spatial data. So we talked about time. What about space? So data in space. You can think of maps and such, but not just maps. But that's a good introduction. So a popular way to view or model data is over time or space. We're focusing on space. Here I give you a nice introduction to spatial, not an introduction, but a definition of spatial data. So it's information about a physical object that can be represented by numerical values in a geographic coordinate system. There's a lot here. This leads to complex data structures because you have to hold the location, size, and shape of an object. They are called geometries, a point, a line, and a polygon. So when I hold a map, you not only have to hold, like an X and a Y coordinate, you have to hold a little bit something more. And so the structures, the actual files that hold this stuff are a little bit more complex than the ones that we're used to. The basic file type that holds this info is called a shapefile, and you'll see it as .shp. And there are many types of these types of files are commonly used in geographic information systems, and so if you've taken a GIS class before, you've definitely used shapefiles before. And there are specialized softwares to deal with these shapefiles or to work with them. And I think the most common is called ArcGIS. It's proprietary, and so you have to pay for it. But there are free versions, and there are sort of ways around having to pay for ArcGIS. Rather, there are other softwares that are similar that you can use for free. Okay, so in R, these objects were typically held in a data frame-like object that holds the geometries in columns, and we call them slots. But we aren't going to worry more than just this slide about how R actually holds them. That's more of an advanced topic that you don't really need to worry about. We just want to see how we can use them. And the package that we want to use these shapefiles with is called SF. So the main package in R for a while to use spatial data or to work with spatial data was called SP, but SP was big and sort of clunky, and so we're going to use a newer and a sort of lighter package. It doesn't have as many dependencies. It doesn't have as many functions in it. It's called SF, which stands for Simple Features. And so Simple Features refers to a formal standard on how objects in the real world can be held on computers. So there are, I don't know nearly enough about it to talk at length, but in the computer science world, there are standards that govern how a lot of different things should be held on computers, and so that's what this is referring to. An SF data object is basically a data frame or tibble that has extra geometry info that is tagging along. So it's going to be easy to work with for you because it's just a data frame or tibble, whatever you want to think about it as, and that just got some extra stuff going with it. Okay. It's not a tidyverse package, so it's not made by the tidyverse people, but it has been sort of adopted by a lot of the tidyverse people. So it's not even tidyverse adjacent like other ones, but it is popular, we'll say. The naming conventions follow what the tidyverse people have tried to do, meaning that it starts with a 2 or 3 letter prefix and then the verb comes after it. So many of these functions begin with ST, something, 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 and ST, of course, stands for spatio-temporal. So spatio for spatial, temporal for time. Okay, and so here's a cheat sheet for SF. Okay, and so here's what SF can do. So there is an stread function that will read in the shape files, and you'll need to do this for the homework that you're going to look at this week. So that's data science homework number 5. You're going to have to read in some shape files. And the important thing to remember is that especially for those homeworks, when you're trying to read in a shape file, the SHP file needs to be with all of the other weird files that I include on D2L. So if you look at D2L, there are 2 different shape files on there, and they have different names. And there are a number of other files that are associated with the shape file, and they all have the same name. And so you want to make sure that when you download and try to use a shape file... Oh, I'm sorry. My dog is unhappy about something. So when you use the shape file, or when you try to use it, you need to have it in the same place as all of those other files, or else it's not going to work. So make a folder on your computer, put them all in the same place at least when you try to use them. So here's a simple... I'm trying to read in some data, and along with the SF package, they included some example shape files. So if you copy and paste this code into your R after you install and library SF, you should, get this. So when you look at NC, which is North Carolina here, so I'm reading in a shapefile of North Carolina, it gives you all of this. And so it gives you lots of information about, it looks like counties down below. Okay. And it also has some extra stuff with it. And so what you can do, if you look at NC, it's a data frame and also an SF object. So it has both of those things going along with it. And so what we can do is, one, you look at your geometry, and so this geometry, this extra thing that is tagging along, is basically drawing out the map, or drawing the edges of the map. And so you can plot these. ggplot2 has support for SF objects, which is wonderful. And so all I have to do is put ggplot. I have to instantiate a ggplot2 instance. And so I do that with the ggplot function, and I put in the NC shape file. Here I pipe it in, but you could just put it in and you run geomsf, and you get this, which you should recognize from your U.S. history class as North Carolina, and all of the counties in North Carolina, or rather their sort of boundaries, right? And so that's what that SF object holds, is not only, it has other information, but it holds these sort of bounding boxes of the counties. Okay, and then you can add stuff to it. So here, although it's not very exciting, I added, I filled in the areas with their area. And so I filled in the counties with their area. And so if you look at the different colors, you can see that gradient is for the area. Okay. And let's see. There are a few specialized objects. So if I went to union all of them, so that's the sort of OR in logic. So if I want to have the union of all of the counties, it takes away all of the inner counties and just leaves the sort of outer bit. And there are other functions like that. Now, to get specifically to maps, there is a package called ggmap, which is fairly popular. And so it might be helpful to add a map, like a Google map, to the background, and you can put points on the Google map. And so there is a function. There's a package called ggmap that interacts with the Google Maps API and other mapping services to pull down map tiles. Okay, and so part of the reason why I'm mentioning this package is that it is very cool. The other one is that my graduate school advisor made this package. And so I'd be remiss if I didn't talk about it. Okay. Now, it became less cool when Google became less cool, and they implemented changes that requires you to sign in to the API and input some credit card information. Now, it is still free, but you have to do all that in case you use it too much, and then it becomes not free. So I understand if that sort of pushes you away. But I have a short example that will show you what ggmap does. So here I can get a Google map of North Carolina. So if we're looking at North Carolina, and I can use that and make a plot of the map. It has some special functions. So I can geocode Shippensburg University, and then I can reverse geocode stuff. And so I reverse geocode this latitude and longitude, and I get 1600 Pennsylvania Avenue, Washington, D.C. And of course, if we were in person, I'd ask everyone, does anyone know that special address there? It's special why? And the answer is that it's the White House. Okay. So anyway, and then I can also find a route from one place to another and plot it on that map. And you can do lots of extra stuff with ggmap. I'm not going to ask you to do anything with ggmap on any assignment because of the weird API stuff. But if you are interested, I will surely help you set up access to the API and actually use ggmap. Okay, and so that's the end of these slides and end of the other data types.